Hello folks, my name is Marcus Meller. I'm a VLSI researcher studying under Dr. James Stein at Oklahoma State University, and I'm also the primary developer behind CharLib, the open source standard cell library characterizer. The goal of this video tutorial is to walk you through the process of getting started with CharLib. We're going to start with a fresh system, and we're going to go all the way to getting a PDK and using CharLib to characterize that PDK. So, in this video, we will talk about what CharLib is and what it isn't. We'll walk through the process of installing CharLib on a fresh system, including its prerequisites like ngSpice. We'll download an open source process design kit, or PDK, using CL. We'll set up a YAML file describing the standard cells in that PDK so that CharLib can find them and know how to characterize them. And finally, we'll use that configuration file to run CharLib and characterize those standard cells. So let's start with what CharLib is and what it isn't. CharLib is a program designed to characterize, that is, measure the electrical properties of, standard cells. What is a standard cell? It's the building block of a digital circuit. When a chip designer is getting ready to manufacture an integrated circuit, or IC, he or she generally likes to have some estimate of how well it's going to work. And that's where characterization comes in. It helps us answer the questions of how much power will that chip design use? How fast will it be able to run? So the way it works is, if I know how fast all of the building blocks, all of the standard cells in my design are, and how much power they will each use at all times, then by looking at how they're connected, I can make an estimate of how my larger chip design will work, how much power it will use, how fast it will be. So, by measuring the timing and power properties of standard cells, I can easily extrapolate and figure out the properties of a big, complicated chip design. This is what CharLib does. You give it a bunch of small standard cells, those building blocks, and it measures their properties through simulation. Okay, so that covers what characterization is. Let's talk about what CharLib is. CharLib is software that is designed to do standard cell characterization. So you give it standard cells, and it measures their properties. Now, something that's very different about how CharLib works compared to other EDA tools that are out there is CharLib's approach is descriptive. With most EDA tools, you write a script in tool control language, or TCL, in order to tell the tool what to do at every point in time. CharLib doesn't work that way. With CharLib, you're going to describe your standard cell library. So you're going to create a configuration YAML file that tells CharLib what your cells are, where the relevant files it needs in order to do simulation live, and what simulation conditions you need to test under. This is a very different approach from the typical tool control language approach. Instead of prescribing, here's what the tool needs to do, you're saying, here's what my standard cells are. So CharLib is also fully open source. That means you can find all of the documentation and information about how to use CharLib, and even look at the source code behind this characterizer, all online. We typically also use ngSpice and Zeiss as our circuit simulation software. Those are also open source programs that you can look at the source code of. But if you do want to, you can write procedures for CharLib that use closed source simulators like Spectre or HSpice. Now, if you don't know what any of that means, don't worry about it. We're going to walk through today how to use CharLib in the typical way with a fully open source flow. So let's start with the process of getting and installing CharLib. So if I go to the documentation here, and let's look at the installation page. That's what I'm interested in right now. So the typical user, the typical approach to working with CharLib is installing from pip. So I'm going to click on that, and I see we have some dependencies first. CharLib requires the following prerequisites. You have to have Python 3.12 or newer, and you have to have an analog circuit simulator. And there's a list right here of the simulators that CharLib supports. So then let's start there. Okay, first thing I'm going to do is open up a terminal. And our first goal here is to install ngSpice. So I'm going to use my Systems Package Manager, and I'm going to install ngSpice. Now, one thing that's tricky here, when you're installing ngSpice, you need to make sure that you have the ngSpice package that includes the shared library. CharLib can run without the shared library, but in my experience, it works a lot better if you have the shared library. So I happen to know that in my case, the package I want is ngSpice devel. Many other distributions of Linux will have a package called, for instance, libngspice or ngSpice dev. But that's the package you'll need to install. You need to make sure you have the ngSpice shared. Okay, and looking here, I see that I already have ngSpice installed. So I've created a new folder here that I'm going to use for this demo. The next thing I want to do is install CharLib itself. So flipping back over to the instructions, I can see that the easiest way to install CharLib is to just use pip to install it directly from GitHub. So I'm going to go ahead and copy that command. And before I do this installation, what I'm going to do in my terminal, I'm going to create a virtual environment. So a virtual environment will help keep my CharLib install isolated from my system set of Python packages. My computer, being a Linux computer, relies on a working install of Python. And I don't want to mess with that. So as much as I can, I'm going to keep this package separated from my system. And I can do that by creating a Python virtual environment. I'm just going to call it vinv, which is just shorthand for virtual environment. But that's what we're going to call it today. You can put whatever string you want there, but I'm just going to call it that. And now when that's done, if I list files, I can see there's my virtual environment. I'm also going to go ahead and activate the virtual environment. Your command to activate the virtual environment may be a little different. If you're on Windows, for instance, there's a command prompt script that you'll have to run, or maybe a PowerShell script, depends on what you're using. I'm using fish shell, so I have to use activate.fish. Right? Now that that's activated, I can see the Python version, the version of the Python interpreter that I'm going to be using for the purposes of this demo. Now, if you are unsure whether you've activated your virtual environment, the easiest way to check is to use the which command and just run which Python. And here I can see this Python interpreter lives in this vn folder. So I should be good to go there. So let's clear the screen. And let's install CharLib. So I'm going to use that command I copied earlier. And what this is going to do is we're going to load up the pip module and then use pip to install the package directly from Git. So what this will do is it will download this package from GitHub. And in particular, we're going to check out version 2, which at the time of recording this is the latest version of CharLib. So let's see that run. So we can see that that was successful and that it installed quite a few packages. So we've got things like, let's scroll this, we got NumPy, that's something that CharLib uses directly. We've got SciPy, Scientific Python. We've got Liberty Parser, which CharLib uses to interact with characterization data. We've got Matplotlib, which CharLib uses to generate its plots. We've also got PySpice, and then finally we have CharLib, which we can see was successfully installed. Okay, so now that we've got CharLib installed, let's test it. Let's make sure we can actually run it. So if I run, I should be able to run the CharLib executable. And let's just try something simple like charlib help. Let's see if we get some help output. Perfect. So in my case, I see the usage information for CharLib. Next, let's download an open source PDK. To do that, I'm going to use the open source program CL. So this is a package manager for open source process design kits. So here I have the FOSSEE Foundation's CL package manager opened. This is an open source PDK version manager. What that means is it'll let me download and install or enable or even manage multiple different versions of PDKs that I have installed on my computer. So let's scroll down to the README. And let's look at what the process looks like here. So I'm not on Debian or Ubuntu, I'm not on RHEL or derivative, I'm not on Mac OS. So I'm going to look right down here at this installation and upgrade section. So let's follow these instructions. It looks pretty simple. I'm just going to install it with pip. Looks like they do want me to use a user flag, which will tell pip to install this to my user folder. I don't actually need that in this case, since we've already decided we're going to use a virtual environment, so I'll leave that off. They also want me to use an upgrade flag, which is handy. What this does is, if you already had CL installed, then this would upgrade the version to the latest version available. Now I'm not sure what this no cache directory is doing for them. Probably they're wanting to make sure that you grab the actual latest released version of CL from online. So that's probably what this is doing here. But we'll go ahead and copy that command. Navigate over to our terminal, and we'll go ahead and run that to install CL. And that's what I was saying. Since I'm in a virtual environment, I can't use the user install. So what I can do then is get rid of those two flags and install CL. Next, let's check whether we've correctly installed CL. And that looks like it was successful as well. We've got some nice version output and a little bit of license text for them. Now that we have this open source PDK manager installed, let's talk about how to use it. So once again, I'm going to flip back over to the README here, and there's a usage section here, which is perfect. That's exactly what I'm looking for. So they talk about how you may need to have a PDK root set. I don't care about that. I'll let them use whatever their default is, which looks like it'll put it under my home directory. It'll put it in a .cl folder. So that seems fine to me. I'll let them use that default. So let's start by listing the available PDKs. And it looks like we're going to do that with this command, cl-ls remote, to list what's on the remote, PDK family. Now in order to use this list command, I do need to know what PDK family I want. In this case, I think I am going to use the GF180MCU PDK. So we'll go ahead and give that a try. So I'll pull up my terminal again, and I will go cl ls remote. What was the syntax there? --pdk family. PDK family, and we want GF180 MCU. Okay, so we see quite a long list pops out here. And I probably just want the very latest version, which looks like it came out the day after Christmas. So this is the version we want. We are going to need that hash, so I will copy that. And let's look back at the README real quick. So on the README, what I want to do is download and enable a PDK. So this is the command I need. CL enable PDK family, and then I need to give it the family that I want, which is GF180MCU, and then the PDK commit hash, which is what I just copied. So let's flip back over to our terminal, and we will go CL enable --PDK family GF180MCU, and then we'll go ahead and paste that hash we copied. This should download and enable that repository for us to use. Okay, it looks like that was successful. We can see that it went and downloaded the PDK from somewhere online. So let's take a look at what we have now. It told us that it was going to put the PDKs in the PDK root, which from before we saw was .cl. So let's see what's in there. I'm going to change directory to that folder. Let's take a look. Okay, so it looks like we have a CL folder, and then we have a couple of links to probably different versions of the GF180MCU PDK. Okay, so let's cd into GF180MCU-A, and let's take a look at what's in here. So I can see there's a couple folders, libs.ref, libs.tech, and then I've got this sources file. That sources file is actually something used by CL, so I don't need to worry about that. But let's take a look at what's in libs.ref. This is probably where I'm going to find my standard cell libraries. So let's change directory into that. And I can see there are 2 standard cell libraries in here. How can I tell? Because they have this SC in the folder name. There's a couple things in here that I care about. Number 1 is these primitives. So in that folder, is probably going to be my transistor models that I'll need to use for GF180. And then these 2 folders, both of these that have SC, standard cells, in the folder name, those are going to be 2 different variants, 2 different libraries of standard cells. We've got a 7-track variant and a 9-track variant. Both of these variants are 5 volt nominal. For now, let's just use the 7T. So let's CD into there. I want to go to the standard cell MCU 7T folder. Let's take a look at what we have. Okay, so there's a SPICE folder, and that's almost certainly exactly what we're looking for. I do want to point out there's also a lib folder in here, and that contains some characterization results, Liberty files. When your semiconductor foundry manufactures a chip, not all of the transistors are going to be exactly the same. You're going to have some cases where they're a little bit faster, but they're more power hungry, or a little bit slower, but more stable. So that's what these FF and SS and TT represent. FF is for your fast but power hungry and less stable transistors. SS is for your slower, more stable, but probably less performant overall transistors. And TT is for typical. So this is typical process corners. This is probably what we're going to target characterizing today. And then the other thing about each of these files is they each have a temperature and they each have a voltage attached to them. So the temperature is going to be the temperature that they are simulated at. So we've got everything in here from 125 degrees Celsius, which is really hot, hotter than most of these semiconductors would actually run in typical use cases. And we've got N40, and you might be able to guess that's negative 40 degrees Celsius. So those are both going to be your extreme cases, your extreme corners of simulation. And then we also have the more typical 25 degrees Celsius. That's about room temperature. So that's what we're going to use for our simulations today. Now a couple other things we have in here. Every one of these has a voltage. So that's going to refer to the supply voltage used when testing and characterizing each of these cells. And they have everything from a really low 1.98 volts all the way up to a really high 5.5 volts. Now this was, if you recall, a nominal 5 volt PDK. So this 25 degrees Celsius, this 5 volt, this is what you consider your nominal characterization data. Now I point this out because these PDKs typically come with characterized data. So CharLib isn't something you're often going to use on your own unless you're generating your own standard cells. So if you are making your own standard cells, CharLib is something you're going to want to use. If you're getting standard cells and using standard cells from a foundry, then this is probably not something you need. But if you need characterization data for a cell of your own devising, your own design, that's when you need to use CharLib. Otherwise, typically the data is already going to be provided by your foundry. Okay, so let's take a look in the SPICE folder now. Let's look at what's in there. So in the SPICE folder, we actually only have one file. Let's take a look at that. Alright, this is what we're looking for. This file contains SPICE subcircuits. Each of these subcircuits is going to have a name. So this one is this long string. Here's like the whole PDK, standard cell library name. And then this is the critical portion, add F. That tells us what this cell does. This is a full adder. So that we have the typical inputs and outputs. We've got an A input, a B input, a C input, and then a C output. So these are your carry input, carry output, and then your sum result. We've also got power and well inputs. So this is going to be your voltage supply. This is going to be your ground supply. And then we have an in well and a P-well voltage. These are going to be our biasing voltages. Typically those are going to be tied to either the supply voltage or the ground voltage, but there are cases where you don't want that as a cell designer, so these are included so that you can vary that. And then we have, within the subcircuit body, we have all of these X whatever, these XM51. These are other subcircuits that we've defined elsewhere. Specifically in this case, these are INFETs, transistors. Right? So we've got NMOS and PMOS. So those are going to be defined in that primitives folder we looked at earlier. But the moral of the story here is this is the file we wanted to find. Because in this file, we have all of our standard cells. So we've got all these cell SPICE models. And these are what we're going to use for simulation. We've got a bunch of different cells in here. But this actually makes our job really easy. And we'll talk about why here in a minute. We've got CharLib installed. We've got CL installed. We've got our PDK downloaded. We know where our SPICE files live. So let's walk through the process of setting up a YAML file for that PDK. So the best place to go if you're wanting to learn how to set up a CharLib YAML file is over to the CharLib documentation. We've got a user guide that walks through the basic flow. We've already found our SPICE netlists here. We know where our analog transistor models are going to be. They're going to be in that primitives folder. We'll look at specifically where they are in a little bit. And we know that we need to make a YAML configuration file. So that's the next step we're on. So what we're going to look at is some examples. Let's look at this OSU 350 example. So here we've got two sections that are important. We've got a settings section and a cells section. Now these examples are really verbose. They specify all the details, even though you probably only need a few of these. So if I pull up our terminal, and let's make a new file here. So I'm going to open my text editor and modify. We'll make it gf180 mcu-a.yaml. So I need two keys to start: a settings key and a cells key. I'm going to split my terminal, and on my second editor I'm going to go into .cl/gf180mcu-a, and we know we need to be in libs.ref. And let's start with our lib name. I think this should be pretty obvious. We want something that reflects the PDK that we're characterizing. So we'll call it gf180mcu-a. Do we need to specify any units? That is the question right now. So the default units for CharLib are going to be time is in nanoseconds, voltage is in volts, current is in microamps, resistance is in ohms, leakage power is in nanowatts, capacitive load is in picofarads, energy is in femtojoules. And I'm going to use a hint here. So what I'm going to do is I'm going to go into one of the existing characterization data files. So where were those? Let's go look in the 7-track standard cell library again. Let's look at one of those typical lib files. For lib/gf180, and let's do a typical 25 degrees Celsius, 5 volts. So this is the typical process corner. Okay, so there's a bunch of nonsense in here for starters. We probably don't care about most of this, but here's some helpful things. We've got a few units. They are using ohms, they're using microwatts. Their current unit differs from the default, so we do need to include units. So I will add the pulling resistance key. Or not pulling resistance, excuse me. What was I thinking? Current. I will add the current unit key, and that's going to be in milliamps, not microamps. Time is okay, voltage is okay, current is okay, capacitance is okay, resistance is okay. And they do specify leakage power in microwatts instead of nanowatts, which is the default. So we'll go ahead and do that. What else do we need? We need to tell CharLib what the names of our SPICE power and ground supplies are. So the defaults here, this is going to be where we look at our SPICE. So we're going to look at the SPICE file. The names for the power supply name, that's going to be VDD. So we're going to add the named nodes key to CharLib here, to the CharLib configuration. We've got a primary ground, and that is VSS. Oh, excuse me, I need to give it the name subkey, and the voltage. Voltage for primary ground is default to 0, so we don't need to worry about that. We'll go ahead and give it the primary power key as well, and that's going to be a name, VDD, and voltage 5 volts. So what we're doing here, we're just describing our standard cell library. Here's where we're, in this case, describing a process corner. This syntax will probably change in the future, so there will be a different syntax for defining the supply voltage. But for now, we use this named nodes syntax to tell CharLib what the name of our ground and power supplies are and what those voltages are. We do also have an in-well and a p-well voltage. So I'm going to flip back over. Let's do this. Let's flip back over to the syntax guide over here. And I'm going to go to the syntax reference, and this is a setting under cell, under settings, under named nodes, and it looks like the key is just in-well. So you see, even me, I'm the creator of this software, and I don't have it all memorized. But that voltage is called VNW. Now actually, if I look over here in the documentation, the in-well key has name VNW, and now I do need to change the voltage here, because it doesn't just track with the primary power. That's something I already ought to change. I don't need to change the name, I do need to change the voltage. And then the p-well, what's the p-well? That's right here. So this is my p-type biasing node. VPW, that matches the library, so I don't need to change that. And 0 volts, so that's already good as well. Now, in fact, while I've got the documentation pulled up, let me look at primary ground and see what the default is for that. Looks like it's also, the name is defaults to VSS, so I don't need that either. This should be all I need here. Okay, but there is one other key I want to add. So going back to the user guide, to those examples, I'm going to add the cell defaults key. And this is going to make my life really easy, because anything in cell defaults gets copied to every single standard cell that I list under cells here. We'll get to that in a minute. So there's a couple things that are going to be common for all the cells. For one, since all cells have SPICE code in this one SPICE file, I need to list the path to this SPICE file as the netlist for every cell. So relative to the current directory, right, this the CharLib directory that I've created for this demo, let's see. So I'm going to want to go to ls. This is just me figuring out where this SPICE file lives. It is cl/gf180mcua libs.ref gf180mcu sc 7-track SPICE, and that's the name of the SPICE file. Okay. So my netlist should be exactly that, right? So we'll just copy and paste that. And then I do have to give it the SPICE file name as well. gf180 mcu fd sc mcu 7t 5 v0.spice. Okay, so I've got that netlist now. And there's probably a few more things we're going to want to add to the cell defaults. So for instance, the models, transistor models, that's going to be a file that lives not in the standard cell library, but instead that lives in this primitives folder of the PDK. So let's cd into that. Alright, I've got two files in here, a GDS and a mag. So those probably aren't what I'm looking for here. We'll go back up a folder and let's see if we can find what we're looking for in libs.tech. So we'll cd into libs.tech. Okay, we've got ngSpice. That's promising. That's probably where our spice models live. Yes, so this is exactly what we're looking for. In particular, we're looking for these files here, these sort of .ngSpice files. And these are going to be our transistor models. So in this case, we do have a list of a couple of different files. And probably within these files, we have different ngSpice libraries. So let me take a look at one of these. I happen to know from experience that this file contains our transistor models. So let's take a look at that. I'm just going to make this a little bit larger for a moment. Yeah, look at this. So from this little documentation string, we've got subcircuits for 3.3 volt NMOS, 6 volt NMOS, etc. Look at all these MOSFET models. These are all transistor models. Here we've got some resistor, some polyresistor models. We've got some MIM caps, some NMOS caps and PMOS caps, some well-based caps. Okay, here's what we're looking for. .lib typical. So probably what we're going to want to use is with our model key in the CharLib configuration file is we're going to want to use a typical library include. So if I go to the syntax reference, if I go to settings, or not settings, but cell, and I look at models, there's a couple different syntaxes that are supported here. So probably what I want to do is use the .lib syntax. .lib, and I am going to need that whole, let's do it this way, let's do a couple of list items. Because I'm not just going to need this file, I'm also going to need that design file. So, and those are both here in this folder. What is my current directory? Okay, so we're going to need home.cl gf180 mcua libs.tech ngSpice, if I can type it right, and then SM141064. So here's my path, and what section do I want? I want the typical section. So we'll do that. And then for this other design.ngSpice file, that probably doesn't have any lib statements. Let's take a look. Once again, I'm going to make that a little larger. Global parameter settings, global switches, corners, etc. So we might, okay, no, this is just defaults that we probably do want. We don't need to use a .lib syntax here. So following the documentation, we're just going to use the path to file syntax because we just want this included as a .include. So I will again type out that whole long awful path. ngSpice and design.ngSpice. Oh, and it looks like I forgot the .ngSpice here as well. So what these will do, what these models files will do is this one's going to be our transistor models, and this will produce a statement in SPICE simulations that will properly include this file using ngSpice's .lib syntax, and it'll pull the typical library, since that's the process corner we're going for. And then this file will just get included with the .include syntax in Spice. Okay, so we've got our net lists, we've got our models. Now all we have to do is add some cells. So let me split these a little more evenly again. And let's go back to that Spice file we were looking at. So it was in libs.ref. And it's in GF180 MCU SC 7-track Spice. Alright, so here's our Spice file. So with the cells portion of this, let's look at another example. Let's go back to the configuration examples. With the cells portion of this file, what we need is a list of cells by name and a list of their functions. So you don't actually need a ton of detail for each of these. You can include the area key if you want the area to pop up in your characterization data. By default, it'll just stick a 0 in there. But what we're going to end up with is going to look something very similar to this, where all you actually need is the functions. So let's give that a go. I've got a GF180 MCU FD. Here, let's just copy these. So here's my cell name. Alright, that's going to add a new cell entry. And all I need to put in here is what my functions are. Now, for the most part, I can probably guess at what these are. I've got 2 inputs and 2 outputs. Or excuse me, 3 inputs, 2 outputs. So I've got an S, which is going to be my sum. So that's probably just an XOR. These in a list syntax. So S is going to be what? A XOR B XOR CI, right? And then for the carry out, CO, that's probably going to be an AND of A and B. Or I guess there is the one situation where you have your input carry can affect that as well. So we'll use a logical OR here to divide these up. I actually think I have it over here already, assuming this implements the same function. Yeah, so the carry is going to be high if I have A and B, or I have CI, my input carry, and one of A or B. Okay, so let's give this a try. I'm going to go ahead and close this over here. Let's just go back to our one split. We should have a working configuration here now, because we've told CharLib, here's the cell I want you to characterize, here's the function that it implements, we've told it where to look for the net lists, we've told it where to look for the transistor models here. Oh, one more thing we need to make sure we add. What are our characterization conditions? So there's 2 inputs we'll need here. A list of slew rates and a list of capacitive loads. So let's look at, I'm going to open up another, oh, let's not do that. Let's open up a new tab. And we'll go back to .cl. Let's go all the way back to that libs.ref. And let's take a look at, in the standard cell library, 7-track. Let's take a look at some of those Liberty files. Let's look at that typical Liberty file again. And let's find our cell in this characterized information. I'm just going to see what slews and what loads they used for their ADF cells. Here's a propagation time and a transition time table. So this is kind of what I'm looking for. So these are the times that they're using. Are these times or these loads? Actually, I'm going to have to look at the lookup table template. Let's look for that. So here's the template. So that first value, the index 1, is the timing, the slew rate, right? The data slew in CharLib terminology. That second result is the output net capacitance. So that's our load. Okay, so then from our first entry here, we can see we've got like 10 slew rates and like 10 loads. So I'm just going to copy these. Probably we won't want all of those. 10 by 10 is a lot of characterization data. But you know what? It doesn't hurt. Let's give it a try. Let's see what we get. Okay, so a couple changes I made to this file. Number one, I did have to write out the full path to this folder. I can't just use the tilde. I forgot about that. Number two, I'm using a few less slews and loads. These are still values that are pulled directly from the other Liberty file, just because if they're using, I'm going to trust whatever values they've picked. And number three, I had used C and then a numeral 0 instead of CO for the carry output. So with those corrections made, we can now continue. So let's run this. And when we run this, we do get a nice little timer. We can see here it's only going to take a couple of minutes, and then we should have some characterization results. Okay, so it's been some time. We've let that characterization run finish, and now it looks like we've got our results file here in this Liberty file. So let's take a look. Here we've got a results directory that was created. So if I want to take a look at that. And here this is a traditional Liberty file format. So we've got, all of our library specifications and whatnot. And then we've got our lookup table templates. And that's going to describe the format for these timing tables. We've got our cell entry, and that's going to have all the details of that cell that we added. Notice we didn't add an area, so it does default to 0 for the area here. And then for each pin, we should have, for each output pin, we have some timing information. So here's our carry out. We've got the details of the function that causes this pin to rise or fall, right? And then we've got sort of timing relationships with each of the input pins in that function. And those are in the form of a lookup table, where the values are given here, the values of the indexes are given here, and then the actual timing values that you can look up with those tables are given right here. So I can actually also generate plots with CharLib by adding the plots key to cell defaults. And the plots key can contain a list of, there's only two types of plots that are available right now, and those are I/O voltage plots and delay surface plots. So if I do go ahead and add both of those, and just for the sake of shortening this run, let's cut off some of those simulations just so this takes a little less time. Okay, now let's run our characterization again. This will overwrite the previous results, but we'll go ahead and do this for now. Okay, and after a couple minutes, that characterization is done as well. So let's take a look at the results. So here, we once again have our results placed in a results directory. If you do want to specify somewhere else for those results to go, you can use the results dir key in the settings. So this will you can tell CharLib where you want it to put the results instead. But by default, it just goes right in the same directory where you ran CharLib, puts it in results directory. Let's take a look. So here we have that Liberty file once again, and we also have a folder for plots. So let's take a look at what's inside of the plots folder. Here we have a folder for each cell that we did our characterization for. So let's look at that. So we have six different PNG plots that are showing the delay surfaces from any particular input to any particular output. All right, and so here we can see the delay surfaces for each simulation type. So we've got cell fall. That's going to be our propagation time from for any situation where the cell's output is going from a logical 1 to a logical 0. We've got cell rise, which is the same thing, but instead of 1 to 0, this is a 0 to 1. We've got the rise transition. So this is the amount of time it takes for the cell's output to rise. And then we've got fall transition, the amount of time it takes for the cell's output to fall. And so we've got a little surface for each of those, and each of these points is going to be defined by one of those, or a pair of indices from the lookup table. So we've got our total output net capacitance, that's how much capacitive load we had on the cell. We've got our input net transition, that's going to be the slew rate of the input signal that we tested with. And then the result of our test is the total delay. So we've got one of these for each path, each input to each output relationship. And so since we have 2 outputs and 3 inputs, we're going to have a total of 6 different plots here. So this one's pretty funky looking. Yeah, usually you don't get quite that kind of character. What this tells me is we're probably approaching some sort of asymptotic behavior along each of these edges here. Well, this would be an interesting case to add some more, probably some more capacitance points to test at and see what this surface actually looks like a little bit better for the cell fall case. Nothing too crazy going on here. So this is the path from B to the carry output. And the carry output in general seems to be very consistent. Yeah, but that sum output, there's some funky stuff going on with the sum output. So these delay plots are they're not very linear. They don't scale exactly with one or the other of these variables. There's something else and something more interesting going on here. And that's why we built this characterization software, right? So this would be a good candidate to add some more points in between. More points to test at than just these 3 or 4 that we have here. Okay, so then we've got from the carry input to the carry output. Once again, nothing too crazy going on here. And the carry input to the sum. And this one looks very heavy. The cell fall case is heavily affected by the input slew rate. There's some pretty interesting stuff going on there. So once again, this is probably a case where it'd be good to add some more values in between these 2 values here. Some more input net transition, more data slew values. And that's probably why, in the original characterization, there were 10 points for each slew and load. Because there is some interesting behavior that's going on here. And it's a little bit hard to tell from these plots. Of course, this same data is what's in the lookup tables in the Liberty file. So there's plenty of other ways to represent that as well. So now we've looked at the delay surface plots. Let's take a look at some of the I/O voltage plots. So once again, we're going to go to results, plots, the name of the cell that we want to see. Let's see what's in the I/O folder. So we've got a bunch of different situations here. Each of these represents one simulation that was run, or at least one simulation that was selected. For each path, we have a particular slew and load combination that we're testing. So these aren't necessarily going to be as interesting as the delay plots, but they can be very helpful for figuring out how we're actually getting our measurements. So let's take a look at those. Once again, we'll pull those up with XViewer. Oh, and we'll just take a look starting at the first one. Okay. So this is, we can see here we're testing the I/O, the voltage of pin A falling from 5 to 0. And this is going to be, the space in between these 2 dotted lines. That's going to be our slew time, our slew rate that we give as an input. What are these dotted lines? These are going to be defined by the rise and fall threshold values. So if we go to our syntax reference, our settings for logic thresholds, these are going to be the low and high thresholds. So a value above 4 in this case is going to be considered a logical high value, logical 1. And a value below 1 is going to be considered a logical 0. So then we can see the output has a nice curve to it. It's not quite as snappy as our simulation inputs are here. And that's what creates these delays, both the transition delay and the propagation delay. So the propagation delay here would be the amount of time from the middle of this slope to the point where we get the middle, where we hit that exactly that falling threshold here. I believe by default falling threshold is 50%. We didn't customize that in our YAML, so that falling threshold is going to be the same here as well. And so this would be a good fall to fall case where we've got our input is falling, and that results in a fall in our output. So the time between this falling threshold here to this falling threshold here is going to give us our propagation delay. And then the amount of time that it takes for the output signal to transition from a logical 1 to a logical 0 is going to give us our transition delay. So this would show up as this amount of time right here would show up as a fall transition in the cell lookup tables in the Liberty file. Let's take a look at another one. Similar sort of thing going on here. Does it look like we have a smaller slew rate? Let's see, let's compare the axes. Both 1e minus 10. So similar scale, so it looks like we have, it looks like that next one's just a lot slower. Slew rate on both of those is 0.02 nanoseconds. So it's just that we have a larger load here, and that takes the output more time to transition, more propagation delay, etc. Let's flip through to find another case. So we're still in the cell fall measurements. Now here's an interesting one. So here we see a very, very snappy response from our cell's output. So we don't even get to do the whole slew. I mean, once we get, basically as soon as we get to that 50% mark, as soon as we get to our rising threshold here, the cell state falls, and it falls rapidly. So this is a really good, really snappy response. And then we have a really quick transition time as well. So yeah, nothing super interesting going on in a lot of these, but sometimes these sorts of plots can be useful to figure out, okay, what exactly happened during my simulation. I don't usually configure CharLib to spit these out. I usually just configure CharLib with delay plots because they're more interesting, and they tell me a lot more about what I need to do when it comes to characterization. Because by looking at those delay plots, let's pull those back up again. By looking at some of these, I mean, this I can say is probably a pretty good result. But this tells me, well, I need more information about what's going on in this space, in slew rate space here, right? I need to know what's going on between this point down here and this point way up here, and then this other point that seems to be further down. It'd be very helpful to have more detail here. And so I know that next time I run simulation, well, I probably ought to add some more slew rates. And likewise for capacitances. The fact that this is so non-linear here, that I've got this weird dip in this red, in the cell fall surface here. And I also seem to have something going on in my fall transition surface. So that tells me it'd be good to have more capacitances, more results here. Or more simulation inputs here, at least. And so I think you get more information out of these plots. These tell you more, these are more directly what's in the Liberty file anyways. So I like these more, personally. But the other ones can be useful, especially if you have weird edge cases that you want to figure out what's going on. Say, maybe you have negative delays in your lookup tables. Well, then those other plots can be really helpful to figure out how in the world did we get a negative delay, that sort of thing. With that, we've covered just about everything that I want to cover in this tutorial. So thank you guys for your attention, and good luck using CharLib out there.